So staying on the same general topic of circumgalactic medium studies, next this morning, we have Ben Snyder, who has joined us this morning, third year from Cal Poly Pomona. Ben's going to tell us about the project he's been working on with Fakhri over the summer, resolving the role of environment in shaping the circumgalactic media around massive galaxies. Go ahead whenever you're ready.
Thank you, Gwen. I'm really excited to tell you all about what Fakhri and I have been working on this summer. So Kevin gave us a nice introduction to the circumgalactic medium, but I'm going to quickly introduce it again. The circumgalactic medium, to put it simply, is just the region surrounding a galaxy. It has no hard boundary, but we typically think of it as within the virial radius, or for most massive galaxies, about 100 kiloparsecs in scale. The CGM contains cool gas, which is crucial to long-term star formation. Many massive galaxies have stopped forming stars, but we still see that cool gas that we think is crucial to star formation within their CGM. So that's one of the main things we're trying to start to answer in this project, is why these galaxies stop forming stars. And one of the things we're looking at is whether the environment, the galactic neighbors of these massive galaxies, could play a role in this. So how do we look at the gas in the circumgalactic medium? The emission from this gas is too faint to study beyond the local universe, so we need a bright background source to study it in absorption. And like we've already seen in Kevin's project, we use quasars, some of the brightest objects that we can observe. Better yet, in this project, we're using a quadruply lensed quasar. So the way this works is if we have our telescopes on the Earth on the right, we have a galaxy, and then behind that we have a quasar. If everything works out just right, the light from this quasar is gravitationally lensed around this massive galaxy, and it produces 4 images of the same quasar on our telescopes. And this is a rare opportunity. These are rare events, and it gives us a unique opportunity to probe the CGM at 4 different locations per galaxy. So this is the lensing system that we're working with. You can see the lensing galaxy in the middle and the 4 sight lines surrounding it. And note the scale here as well. Okay, so after that bit of introduction, I'm going to take you through what we've done to characterize the galaxies in this field, first by finding their redshifts, and then determining their properties through spectral indices. Then I'm going to tell you how we search for CGM gas, and then I'll take you through our results. Finding galaxy redshifts. So we use data from the MUSE spectrograph on the Very Large Telescope in Chile, and MUSE is an integral field spectrograph. So what that means is we don't have to use slit masks or anything. We don't have to have any pre-knowledge of where these galaxies are. We get spectral information from each individual pixel on our field. So that's a huge advantage, because we can just take the spectra of any galaxies we want in this field. So how do we actually find the redshifts? Say we have a galaxy spectrum on the right here, wavelength on the x-axis, flux density on the y-axis. So we use a technique called principal component analysis cross-correlation. So basically we have these eigenspectra templates taken from the Sloan Digital Sky Survey, and we make a linear combination of those to make a model to try and fit this spectrum. And we do that at a bunch of different trial redshift values. And then wherever the model fits the data the best, that is the true redshift of the galaxy. So as you can see, when we plot the best model, it fits this spectrum quite nicely, apart from some of these skylines, which we have masked out. Okay, so when we do that, what do we find? This is our field once again. We did this for 9 galaxies in this field, and these are the redshifts that we came up with. You can see these are color-coded by group. And I'll explain while that these 3 galaxies that are highlighted, those are important because those are what we found to be massive non-star forming galaxies that we care about why they've stopped forming stars. And I'll explain how we know that in a bit. And these redshifts can also be converted to relative line of sight velocity. So for instance, this galaxy is moving 180 kilometers per second away from the lens, just to give you an idea of the scale here. Okay, so analyzing the galaxy spectra. So first thing I need you to introduce here is equivalent width. So say we have a spectral feature that we're interested in. So to find the equivalent width, what we do is we have to normalize the continuum level down to 1, and then we just take the integral of that spectral feature. This can be done for emission lines as well as absorption lines. And that's a way to quantify the strength of the spectral features, basically. Okay, so the two things we use the galaxy spectra to estimate are this stellar population ages and the instantaneous star formation rates of these galaxies. For stellar population age, one of the things we use is the D4000 index, which essentially quantifies how big is this jump here. At rest wavelength 4,000 angstroms, for most galaxies, you'll see a jump up. And if the galaxy has a lot of old red stars, that jump is going to be bigger. If it has a lot of young blue stars, that jump is going to be smaller. And then also we look at the hydrogen delta line and its equivalent width. So you can see how these vary here. D4000 strictly increases with age, whereas the hydrogen delta curve is a bit more complicated because hydrogen delta is sensitive to star formation within the last billion years. And then for the instantaneous star formation rate, we're looking at the oxygen 2 emission line. Okay, so when we did this for these galaxies, that's how we know that these 3 galaxies are old and non-star forming. And we also took from the literature that they are massive as well. So these are the galaxies we're interested in learning about why they've stopped forming stars. And these are the galaxies that we'll use as references when we actually probe the circumgalactic medium. So how do we actually look for gas in the circumgalactic medium? So the quasar spectra were taken from the Magellan telescopes and the Mike Eshel spectrograph, which is a very high resolution spectrograph. And this is an example of what a plot looks like for when we're actually looking for the gas. So the columns here correspond to the 4 sight lines of the quasar labeled on the right, and then the rows correspond to a couple different species that we're looking at. And then here, for the lens system, we found absorption along the A2 sight line only. You can see those dips here, and the two separate dips, that just corresponds to 2 different gas clouds along this line of sight. And if we detect absorption in 1 out of 4 sight lines, we can use that to estimate the covering fraction, which is basically just the area of the projected area of the CGM covered by the gas. This is a very rough estimate because we only have 4 sight lines to estimate this area, but this will be important later. Okay, so how do we quantify how much gas we see? Well, like before, we can find the equivalent width, and we can directly convert that to apparent column density, which is a very good estimator of column density. But what is column density? You can imagine a thin column piercing one of these sight lines, and column density is essentially the number of atoms per column, because as astronomers, we don't have access to the 3rd dimension. We only see 2D images, so the physical quantity that we can report is column density. Okay, so what did we actually find? On this plot, we have on the x-axis projected distance from the galaxy. That's the same thing as the impact parameter you saw from Kevin's presentation. And then the y-axis, we have the ratio of magnesium-2 to iron-2 column densities. The black data points here are from Fakhri's previous work, and the colored ones are this project. And you'll note that we have multiple data points per galaxy. That's because we have 4 different sight lines, so you can have multiple detections per galaxy. So the thing to note here is the downward trend. As we go further and further away from the galaxy, we see less iron compared to magnesium. So iron comes from type 1a supernovae. This is telling us that these supernovae are slowly spreading out iron throughout the galaxy. And that's a sign that a lot of the chemical enrichment in the circumgalactic media of massive galaxies is coming from within the galaxy itself. And then as far as the environment shaping the CGM, on the x-axis here, we have quantified the environment as the number of known neighbors within 500 kiloparsecs. The top panel is the column density of magnesium-2, which is essentially telling us how much cool gas we find. And then the bottom panel is the covering fraction that I mentioned earlier. So how much area this gas covers. And we see downward trends in both of these plots. So the denser the environment, we see less cool gas, and we see it in fewer places. So what do these results tell us? Well, for the declining iron to magnesium ratio with projected distance, this tells us that there's significant enrichment from within the massive galaxies themselves, as opposed to the broader intergalactic medium. And these type 1a supernovae that I mentioned, they might actually play a role in the lack of star formation because they inject energy and momenta that could prevent gas from cooling. And then the less cool gas in less places, what does that tell us? Well, it's possible that in a denser environment, the neighbors could be spreading the gas out due to tidal forces and preventing it from clumping up and forming stars. Or the gas could just be in a higher ionization state, which would mean a higher temperature, which would also quench star formation. So in the future, we're going to look at more lens systems, do pretty similar stuff, because we really need more data to confirm these trends and really find out more about why these galaxies have stopped forming stars. Thank you for listening. I'm happy to take questions at this point.
Great. Very nice job, Ben. Johanna, do you have a question?
Yes. So on this slide, the first point, the declining magnesium to or iron to magnesium 2 ratio, that indicates CGM enrichment from within massive galaxies. I guess I was wondering, what would it look like if that enrichment wasn't coming from the massive galaxies? Like, what different trends might tell you?
All right, that's a good question. So basically, the way we know that it's coming from within massive galaxies is this downward trend is consistent with the iron slowly spreading out across the CGM. So if the enrichment came from the intergalactic medium, we might expect a more flat curve where
okay,
a more similar density all around.
Got it. Okay, thank you.
Yeah, good. Thanks for the question.
Wonderful, thank you. Do we have another question? So I have actually a question for Ben. Oh, Alex has a question. I've already talked to Ben a bunch, so Alex, go ahead.
This is really, I'm wondering, I missed the distance to which you can cover. Is that consistent with sort of type 1As being like, they have some sort of, I'm not sure what their distance distribution we might expect for type 1As to be going off, but is that match up with what you expect? Like where they're exploding is where you see the extent of this?
I'm sorry, I'm a little unclear on the question.
Yeah, sorry, it's because it was poorly phrased. I guess what I'm wondering is there a comparison that could be made between sort of how far we actually see type 1A supernova relative to the center of the galaxy and sort of where you see the iron. Does that make sense?
Like how far the iron can go?
I guess I'm wondering if type 1a supernovae, I don't actually know for sure where they explode, but I assume they're not all, and there must be some distance distribution from the galaxy. And I'm wondering if you have an idea of how those might compare.
Yeah, so we didn't really look into that at all, really, because the supernovae, we can generally assume that they're coming from within the galaxies themselves, and so I'm not sure. Sorry, I'm not sure if I have a good answer for that. I'm realizing.
No, that's very helpful. Thanks.
All right, thank you, Ben. That was excellent. I think we should go ahead and move on to the next speaker, but very nice job.